This lecture is a brief introduction to deep learning. This matter will be covered in more detail in a specific course next semester, but I wanted to end this machine learning course with a broad idea of this increasingly important field in machine learning. So I'm going to talk a bit about the evolution, the history of neural networks, and explain why deep learning started to have success so recently in recent years. I'm also going to talk about the main advantages of deep learning and a problem that has been one of the difficulties for training deep neural networks, the vanishing gradients problem, and how it has been mostly solved in recent years. And then I'm going to focus as an example of a type of architecture and for deep learning, which are autoencoders that can be used for unsupervised learning. This is just one example of many different architectures. I choose this one because I like autoencoders personally, and also because they can illustrate the versatility of artificial neural networks, especially deep neural networks. So the idea of trying to model neurons mathematically and in computers is very old. It's even older than modern artificial intelligence, around 1943. And the algorithm for trying to train a single neuron to learn was proposed in 1958 by Rosenblatt. So using neurons to learn is something that is already very old nowadays. But the problem is that using just one neuron is simply a linear model. And so this, starting from the early 1970s, late 1960s, there was this bit of a disappointment with artificial intelligence and with machine learning, this part that was so promising at first. So we talk about this winter of artificial intelligence around between 1960s, late 1960s and 1980s. In which there was a huge disappointment with all the promises that artificial intelligence had made before. However, during this time, the backpropagation algorithm started appearing in other contexts, and in mid-1980s, it was first used to train multi-layer networks. So this gave the possibility of training layers of neurons, and this now goes beyond the simple linear model, because it can do nonlinear transformations and does learn to classify data more complexly. Also in the 1980s, especially with things like the kernel trick for support vector machine, there was a shift from that artificial intelligence based on logic and symbolic reasoning, knowledge representation, and so on, and into machine learning, because now these algorithms started to become more powerful, more useful. And the idea here is that humans do feature extraction. They select what kind of features we want to use, for example, for support vector machines, random forests, things like that. And then there is some transformation in the model that allows the classification at the end, whatever we want to learn, to be done with a linear classifier. And support vector machines with the kernel trick are an excellent example of this, because the support vector machine, as you know, is a linear classifier. However, with the kernel trick, we are doing the linear classification implicitly in that higher dimensional space after the transformation of the data. So this is something that increases a lot the power of these models, but still it requires that humans select the features and produce a neat table with all the different features, so that we have the vectors inputting into this transformation, and then the model will be trained to produce the right classification. Now, in parallel with this, there was also the beginning of using multi-layer and convolution networks for handling images. For example, for processing checks, handwritten checks. This was one application. Another one was for processing the postal codes for addresses in the postal services. And in 1998, the famous MNIST database with the handwritten digits was created. So at this time, there was the beginning of this practice of creating libraries, databases, benchmarks, competitions, and so on to improve machine learning. And also, more recently, in the early 2000s, there was this first attempt to train deep neural networks, which means that we have artificial neural networks that have many layers, and these are harder to train because the more layers you have, the more difficulty there is in propagating the error and adjusting the parameters. But in 2007, Hinton proposed a method for pre-training individual layers in an unsupervised manner using autoencoders that we're going to see a bit later on, and then stacking them and just doing a final fine-tuning with backpropagation. So this worked more or less in some cases, and it was the first instances of training deep neural networks. But in 2011, there was this big jump, big innovation of the rectified linear unit. I'm going to explain this a bit more when I talk about the vanishing gradients problem, but this made a big difference in how we can train deep neural networks. Also, the increase in interest and the performance of these models led to the creation of specific hardware for training neural networks, such as the Intel Nirvana processor and the Google TPUs that now you can even use them if you use Google Colab. You can use these from the cloud, from Google servers. So the big change here is that instead of having that approach where the human selects features, there is some nonlinear transformation, and then finally you have the last bit with the linear classifier, for example, in a support vector machine. What you can do with deep neural networks is that since you're stacking many nonlinear transformations and the network itself is learning how to do those transformations, you can just input the raw data, and whatever features may be useful there, we let the deep neural network find them. So this is an illustration of stacks in a convolutional neural network. Convolutional neural networks are used, for example, for image processing, and they can different convolutional kernels can learn to identify different patterns. But as we are in the first layers, they respond to simple patterns like edges and different orientations of the edges and contrasts in the image. But as we build on and we create layers that are receiving as input the output of these filters, they start to be able to respond to more complex patterns in the image. And as we go deeper and deeper into the network, the greater the complexity of the patterns that these filters are responding to. So we start, as we move along the network, to get better and better representations that capture increasingly complex patterns, so that at the end what is supplied to the final layer that does the classification is already a selection of the best features to make the classification that we want. So the idea is that with deep neural networks we automate this process of feature extraction, and the network itself learns how to do it. We saw these examples, how these transformation allow us to solve problems that are not linearly solvable, the points are not linearly separable. In the case, for example, the exclusive OR problem is a very simple example of this. You cannot separate the blue and the red with a single straight line in the original space. But when the first layer learns a useful representation and puts both red points there at the corner, now it's very easy to draw a straight line and separate the two classes. So the idea here is that the original data, if we use this representation where we have the feature 1 and feature 2 and the label that we want to predict. So basically, if we have false and with false, this is false. If we have true and true, this is false. But if we have false and true or true and false, then both must be true. So this is the original representation. But what the network learns in the hidden layer is a different representation of the data, where those that must be output as false have different values on the features, but those that must be output as 1 have both of the features at false, at 0. So this creates this different representation here where linear classification is possible. This is just a very simple example with one hidden layer, but we can, if we have more complex data, we can add hidden layers, and as the representation changes, it becomes easier and easier to solve the problem at the end of the network. So why did not this work at the beginning, so in the 1970s, 1960s, and so on? There are some aspects here that prevented deep learning from being successful in the beginning. So one thing that we could see is the amount of data available. In 2006, there was this this computer vision competition using this data set that had about 50 images per category, so ranging from 40 to 800, but on average around 50, and had 100 categories of different objects. And classical computer vision models could classify the test set with around making one mistake every 4 images or something like that. And these were the best models that could be used for solving this problem. Also at that time, the computers were not as fast as we have now, and with as much memory, the graphical cards and so on, but there was this constraint that the data set was not very large. When we go to 2012 with the ImageNet classification problem, this is a set of more than 1 million images in 1,000 categories, so we have around 1,000 images per category. And now also by this time there was a widespread use of graphic processing units for general purposes, so we could use the GPUs for computation. And in this case, large convolution networks became dominant. So the classical computer vision approaches were no longer as effective as large convolution networks. And one idea here is that if you have small amounts of data, then those classical machine learning approaches work fairly well. And very powerful models like deep neural networks, which have huge number of parameters, basically just result in overfitting. You cannot train them properly with small data sets. So you don't have a good performance of deep learning with small data sets. But the classical simpler models soon reach a limit on how well they can perform in complex problems. But as we increase the size of the data set, the performance of deep learning starts to increase. And at some point, for example, here in this case, then deep learning starts to perform much better than the other classical models because we have very large amounts of data. Also, deep learning is very computationally demanding, so we need good machinery to make it work. And as you can see from this point onwards, deep convolutional neural networks always won these competitions. So we have in 2012, 13, 14, 15, and so on, all the way to the present, the error rate on the top 5 options started to reduce continuously. This top 5 error rate means that one of the top 5 of the 1,000 categories that the network is presenting. So there is an object, an image presented to the network, and the network will sort the categories from the most likely to the least likely. And what we're counting is if the correct answer is among the top 5 of the 1,000 possibilities. So in this case, in 2012, 15% were out of the top 5, so 85% were within the top 5, but then the error rate started diminishing, and by this time we are reaching the rate of error that humans also can make when they classify images. So at some point you start having deep neural networks making more or less the same fraction of errors, as the actual data may have errors in the labels. So it's becoming difficult to actually improve much these last percentage points. But the main point here is that the classical computer vision approach was completely superseded by deep neural networks. And this is an example of a deep neural network, GoogleNet, which is composed. These rectangles here represent blocks, layers of neurons. There are these inception blocks that do some parallel convolutions and then merge them together and do pooling and things like that. So we have several of these inception blocks. There are these path to classification layers here, even in the middle of the network. The idea here was that this would improve the learning of these parts. So even though the classification used is this one at the end, the error is also propagated backwards from these points, so that these layers improve in the speed of learning. But what I wanted to point out here is not only the complexity of this network with a large number of neurons with many, a large number of layers with many neurons in these layers, but also to illustrate the versatility of the architectures, the kinds of things that we can do. It's not merely having something feed forward, entering at one end and exiting at the other, but we can do very complex architectures by linking together these different modules and blocks. And what this gives us is a huge ability of the network to learn how to extract the proper features. This classical approach to machine learning would involve feature engineering, where depending on the application, the practitioner, the individuals would have to solve this problem of extracting features from the data in order to have some table to feed into support vector machines, random forests, things like that. So in text mining, there are these techniques of creating vectors indicating whether or not some words appear. We can cluster similar examples and then use those as features, the clusters, to try to simplify the data. We can, in image segmentation, do things like detecting edges, measuring thresholds, histograms of colors, and so on. So basically, these techniques are not only demanding from the humans, but also usually take a long time to perfect, to find out how to extract the useful features for any particular kind of problem. But the goal in artificial intelligence should be for the computer to solve these problems for us, and not having us trying to solve each individual problem. And this is very important when we need our systems to answer quickly to changing conditions. For example, in adversarial systems like detecting credit fraud or fake accounts in social media, things like that, if we develop some system that starts working, then people who are trying to deceive us will change their approach in order to work around our system. So we need, in these kinds of situations, we need to have a very rapid response to these changes. And if the humans need to find the correct features and then work with some machine learning model that takes those tables, does a nonlinear transformation just to classify, then this takes too long to be able to be that responsive. Deep learning solves these problems because all of those steps involved in feature extraction are being learned by a stack of layers that do many nonlinear transformations stacked in order to extract the correct features. So we saw this idea of the power of nonlinear expansion when we looked at support vector machines, for example, where the ability to transform the data into a different representation allows us to solve problems, classification problems that otherwise could not be solved with a linear classification. But with deep artificial neural networks, these layers of nonlinear responses are all learning the sets of parameters that they need. So not only are they extremely nonlinear in these transformations because we are stacking many different transformations, but they are learned transformations during the training process. And this is what allows the deep neural networks to find the correct patterns in order to extract the features for the final classification step. This is more efficient than just trying to do a single nonlinear transformation, because even though we could in theory do this with one layer, because in theory a single layer, a single hidden layer in a neural network can arbitrarily approximate any function locally. So we could theoretically, using a single layer, find any kind of transformation that would allow us to go from the input data to whatever result we want. The problem is that even though in theory this would work, we don't know how many neurons we would need on this single layer. And as we stack layers, we're getting an increasingly power of oscillation, of changing rapidly from one value to the other, depending on small changes on the inputs. And these oscillations are related to the Vapnik-Chevonenkis dimension, which we saw can be used to measure the power of a classifier. So this is one reason why stacking many layers ends up being better than just using one huge layer or one huge transformation into a very large space, for example. However, one problem with training deep neural networks is that as we stack the layers one in front of the other, and we need to propagate the error from the last layer to each of the hidden layers, we need to keep multiplying all of these derivatives. So if you recall from backpropagation, we are using the chain rule to compute the derivative of the error function that we have at the end as a function with respect to each particular weight that we need to update. But as we go deeper and deeper in the network, as we go back in the hidden layers, we need to keep multiplying all of these partial derivatives in order to chain the derivative with respect to each layer. And since all of these products, all of these multiplications can involve numbers that are small, if some of these derivatives approach zero, then eventually we get a result that is very close to zero. So the problem here is that as the derivatives somewhere approach zero, as we keep multiplying everything, the gradient information disappears, and this is called the vanishing gradient problem. As the gradient information disappears, we no longer know how to update the weights, and the training starts to stop because those weights are not properly changed. And this is happens a lot with activations such as sigmoid and hyperbolic tangent and things like that that were classically used. So you can experiment this. For instance, if you go here to the TensorBoard playground, I'll leave the link at the end. You can choose data sets and the size of the network that you want to experiment with and the kind of activation function that you're going to use on the neurons, and you can experiment, for example, with the sigmoid activation. If you use one hidden layer to classify this data set, it works well. This more complex data set doesn't work well with one hidden layer, but if you increase the depth and if you add more hidden layers, then training starts to slow down very much, and it doesn't seem to be able to solve this problem. So at some point, if we have these kinds of activations that saturate, the derivatives start to approach zero, and the gradient information is no longer propagated properly to the first layers. So training stops because of this. And the reason for this is that if you look at the shape of the sigmoid activation function, as we reach higher values here, the derivative starts to approach zero because this function will grow increasingly closer to 1, but it's never larger than 1. So here at these large values of x, the y value is almost constant. And as this saturates and derivative becomes close to 0, then that chain rule where we are multiplying the derivatives starts to not work to train the parameters, because the product becomes very close to 0 and we don't have gradient information. So one big change that occurred in 2011 was the use of these rectified linear units. So instead of being like the sigmoid that saturates here at 1, or the hyperbolic tangent, for example, which was also used, that goes from -1 to 1, but has the same kind of shape, the rectified linear unit is just this elbow. So if you're below 0, it's 0, but if it's firing, then it's just outputting the same as the input. And this break here between this part and this part is enough to give it that non-linearity property that we need for nonlinear transformations. Note that if the output was just the input, this would be just a linear transformation, a trivial linear transformation, and it would not work for the neural network. So we need to have this corner here, this elbow. But because of this very simple function, when the neuron is firing, when it's not 0, then the derivative is always 1. There is no vanishing gradient problem in this case, because the derivative will not vanish to 0. And this allows us to work easily with deeper networks. So if we use a sigmoid activation with 3 layers in this case, we can train, for example, here nearly 1500 epochs, and still there is no very noticeable improvement in the output. But if we change for a rectified linear unit, even after less than 300 epochs, we already have a good classification here. So you can experiment with this and see the difference, because in this case we are not blocking or stopping learning due to the vanishing gradients problem. We always have information about how to change the weights, and learning proceeds until the error function is very small. So even if we add more layers, with 4 hidden layers, for example, it still works. And this is basically one of the big answers to the problem of how to train deep neural networks. Okay, so now I'm going to briefly talk about one type of artificial neural network architecture, which are the autoencoders, which I find particularly interesting because we don't need to have these labeled sets of data in order to learn with autoencoders. The idea is that we are creating an artificial neural network that has as an output the same as the input. So what we are doing is, when we pass some input through the network, we are measuring the error by comparing the output of the network with the input. So we don't need additional labels. Whatever the input is, can be these cat images, for example, we just measure how different the output is from the input. And this may not seem something that is very interesting, because we are just learning to do some transformation on some transformation that brings us back to the original input. But what makes it interesting are these 2 transformations that we are composing here. Because on one hand, one half of the network is transforming the input into some particular encoding, this latent space, from which the other part of the network can extract the original image. So this encoding here must somehow retain enough information about the data in order for the decoder to be able to reconstitute the original image. So this is the important thing about autoencoders, whatever is being done here in the middle, and the representation that we are learning about the input. So as long as we can force the autoencoder to do something useful to the data, we can use this architecture where we just input something and try to output the same thing, We don't need labels because we can always compare the output to the input to have the error function. But we use this to force the artificial neural network to learn a useful representation. And we can do this in many different ways. As long as we create some bottleneck to the information that forces the network to learn a better representation instead of just copying everything from the beginning to the end. Now, this one of the interesting things about autoencoders is that it seems to approximate a bit more the way humans learn than when we look at classifiers and things like that. Because usually we do not spend our time learning with labeled examples. We look at things, we hear things and so on, and we find some internal representations in our brains that then allow us very easily to apply labels to different categories because the categories are already formed in our brains. So let's see some different types of autoencoders. One that is very obvious is the Undercomplete Autoencoder, where we are creating a hidden representation that has a lower dimension than the input. So basically this forces the network to learn a more compact representation. We minimize this loss function that compares the input to the output of the network, which is basically the output of the encoder fed into the decoder, and then we take the output of the decoder and compare it with the input. And this leads to dimensionality reduction. It's a good way of doing, for example, manifold learning. But since we have nonlinear transformations, we have something that is more powerful than what we would have, for example, with principal component analysis. Of course, if we have a very, very large network, there is a problem that the actual information about the examples may start to become encoded in the weights of the encoder and decoder, and the latent representation can be mostly useless. So, for example, you imagine that we have a very large network. The latent representation is just a number, and depending on the number, the decoder would output each particular image because it has all the information stored in its weight. So this would not be useful. We need to have to pay attention to overfitting too in this case. But if we can have an adequate network, then we can have good representations in the hidden layer. One classic example of this is Mitchell's autoencoder, in which the input is a vector of 8 numbers, one of which is 1 and the other are 0. So we have 8 different examples in our data. And the output must be exactly the same thing, and we are training the autoencoder to encode these numbers as 3 values only. And here we see these combinations of high, low, 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 high, high, and things like that, which are like the combinations of 3 bits, which can be low or high, and we have the 8 combinations. So basically, we have a binary representation of the 8 different examples that we have in our data set. So this is a very simple example, but we can have more complicated examples by looking at images or any kind of realistic data. We can also do overcomplete autoencoders. These by itself do not seem to be a good idea because we have a hidden representation that has a higher dimension than the input and the output, but we can impose different constraints on the autoencoder using regularization. For example, a contractive autoencoder imposes also this term to the loss function that is a penalty that depends on the gradient of or the derivatives of the activation of the neurons with respect to the values of the input. So what we are doing this is that we are trying to make the activation of the neurons in the hidden layer less sensitive to small variations of the input, which results in a more robust encoding, but it restricts and reduces the the freedom with which the network can adapt to the data. So we can do this even without using undercompleteness. Of course, we can combine this. We can do an undercomplete autoencoder that is also contractive, but we could, in theory, even use this with an overcomplete autoencoder as long as we apply this regularization. So basically, we are restricting the freedom of the network in a different ways. And in this case, in a contractive autoencoder, we are trying to make the representation robust to small variations in the input. This is an example of comparing the kind of sensitivity to pixels that we have in principal component analysis, for example, where we have here, these are the representations of the leading values after this dimensionality reduction with principal component analysis and with the contractive autoencoder. So the idea here, without going into detail, is that the contractive autoencoder, by imposing that constraint that we must be robust to small changes in the input, really the representation focuses on important aspects of those images. So you can see here for the handwritten 0, the different response at different filters in the convolution layer there, and for the horse here. And if we look at the components, for example, of principal component analysis, then things are really very messy. So comparatively, the contractive autoencoder can find more useful patterns, more useful data in the images or the examples that we presented. We can also, with sparse autoencoders, force the number of activations on the hidden layers to be small. So basically, we consider some fraction that we want, some probability of firing. For example, 10%, this would be 0.1. Then we would want only 10% of the neurons on the hidden layer to be active for any example that we present. And we can do this by adding to the loss function, the error function that we are using, we add a term that compares the activation of the neurons in the hidden layer with this probability that we want, using, for example, the Kullback-Leibler divergence. We saw this previously with TSNE, for example, and this is a measure of the divergence between probability distributions. So when we look at what's happening when we present the examples to the network and what we would like to be happening in the number of activations that we have, we can measure that as an additional factor, an additional penalty for the loss function, and so coerce the network into only firing a few neurons at a time when we present examples. So what happens here is that the filters that we are producing, the neurons that are responding to different patterns, tend to specialize on specific patterns that we find in our examples. So this is an illustration. This is trained on images that are 10 by 10 pixels. And we also have 100 neurons on the hidden layer. So we can represent that also as a 10 by 10 grid here. And here you see the kind of image that maximizes the response of each neuron in the hidden layer. What are the patterns in the image that maximize the response? And you see that the different neurons are specializing in different kinds of patterns in the image, because we are forcing the encoding to be composed for each example only of a small subset of neurons firing. So they have to specialize in finding informative patterns in the images. We can also train autoencoders with noisy data. So instead of just putting the same input as the output, we can degrade the input, for example, adding random noise, and then force the autoencoder to denoise the image. And this means that the representation becomes more robust with respect to small changes in the input. And this can be used either for training the autoencoder to denoise the input or to improve the representation. Variational autoencoders are a kind of autoencoder that is very different from the rest, in which what we are doing here is training the encoder to give us, for each image, the parameters of some random distributions, for example, means and standard deviations of Gaussian distributions. And then the decoder will sample a set of values from this distribution at random and try to replicate the image as close as possible. So this requires a bit of a trick here, because we have this step where we are doing random sampling of the values there, and so we cannot do backpropagation across a random sample. But there is this reparameterization trick where we just use the mean and the standard deviation as part of the network, so multiplying and summing the two. And what we're doing is we are multiplying the standard deviation by a random number, epsilon here, drawn with a Gaussian distribution of 0 mean and 1 standard deviation. So this means that backpropagation cannot go this way because we are drawing this at random, but it doesn't matter because we don't have parameters to adjust here. It can go through the rest of the network in the mean and the standard deviation and all the encoder, because that part just uses these operations. But using this trick, we can actually create a generative encoder that, given some example, can produce the parameters for a random distribution that will then create similar images in the decoder. And this means that once we have the decoder trained, we can input random values with some distributions and generate new images that are similar to the ones that we input there. This is an example of the kind of results that we have. This is a variational autoencoder, the result of a variational autoencoder trained with the MNIST dataset, which has these handwritten digits. And we have the autoencoder learned two random distributions depending on the input. And by setting the values of the mean and standard deviation of these two, we have two independent aspects of the number that is output. One of them determines what the digit is, if it's 8, 7, 6, 9, something like that. And the other one determines the style in which it is written. So by choosing a value from this distribution and another from this distribution, we can use the combinations to write, for example, a 9 in bold, or here more slanted, or 4 or something like that, and use the combinations. The same things for images of faces with different kinds of content and the different person and so on. And we can deconvolute these different aspects into the different distributions learned here on the encoder. So then we have a way of generating new data with the attributes that we want by adjusting the parameters here at the entrance of the decoder part. Of course, this can usually, when we deal with images, these are fully convolutional autoencoders. These convolutional layers are two-dimensional layers of convolutions, where we can imagine that we have a single neuron that is scanning the input and producing a feature map, a map of activations based on the patterns in the input. So these kinds of networks are very used for images, because images have this two-dimensional structure, and the network adapts very well to that kind of structure. And one interesting example of what we can do with autoencoders is the deepfakes. You probably heard about this. And this is one example of how we can do that. So we have here Jimmy Fallon and John Oliver. We take a large number of images of their faces from videos, for example, and we train autoencoders by feeding in the face with some distortions. Note that there were some random distortions applied to the faces here. And we are training an encoder to produce some particular encoding, and then a decoder to obtain the original image before the distortions. So the idea is that this autoencoder learns to fix distortions and put the image correctly. And in this case, we are using the encoder and coupling it to a specific decoder for Jimmy Fallon. So that generates the face of Jimmy Fallon. And in parallel, we are training the same thing with images from John Oliver, where we are using the same encoder, but we are using a different decoder for John Oliver. So basically, this encoder is learning a common representation of images of Jimmy Fallon and John Oliver, but these decoders are specialized in generating images either of Jimmy Fallon or John Oliver. So what happens when we use the encoder to encode images from Jimmy Fallon, which is the original video, but then we use the John Oliver decoder to reconstruct the image. And what we have is that now we have John Oliver replacing Jimmy Fallon in the video. So this can be, the interesting thing here is that we don't need to be labeling data. All we need is a large number of images from each person. And then we train these three different parts, the common encoder for the two and one specialized decoder for each of them. And by coupling the encoder, the images from one and the decoder from the other, we automate the transformation of the faces. So this is an example of how deep fakes can be done with deep neural networks. So to sum up, we saw this again, the importance of nonlinear transformations, but in the case of deep learning, we are stacking a large number of trainable nonlinear transformations, and this is what allows us to deal with unstructured data, with data that is not a set of chosen features in a neat table, but rather raw data that can be very complex, like images, sounds, text documents, and so on. The recent success of deep learning is due in part to some specific methods and techniques like rectified linear units, like frameworks for doing all the backpropagation and automating the differentiation and so on, but also because of the size of the data available and innovations in hardware. So all of these things combined make deep learning a success nowadays, whereas it was not very feasible even say 20 years ago. There are many applications, an increasing number of applications. So basically everything in machine learning nowadays, if we have enough data, someone can do with deep learning. And I just focused in autoencoders because they are my favorite type of architecture, but there are lots of different architectures, recurrent networks for dealing with time series. Those convolutional networks for image processing have many different types of tricks and modules and architectures. Transformers also deal with sequential data and so on. So there are lots of things we can do, because when you have a deep and complex network of layers of neurons, you can put them together in many different ways and build very different architectures with that. So if you want to read a bit more on this, I recommend this paper from 2015 on Nature by these important people in deep learning. So basically the founders of deep learning. And also, if you want to experiment, you can go to the TensorFlow playground, and you have that simple interface where you can choose data sets and activation functions and the number of layers, and you see what the network is learning visually during using those examples.